Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a problem on Reynolds model law. So, in our last video lecture, we have discussed the theory part regarding the Reynolds model law, and based on that procedure or techniques, we'll solve this problem. So here I have taken a question. A pipe of diameter 1.5 meter is required to transport an oil of specific gravity 0.9 and viscosity 3 into 10 to the power minus 2 poise at the rate of 3000 liter per second. The tests were conducted on a 15 centimeter diameter pipe using water at 20 degrees centigrade. Find the velocity and the rate of flow in the model. Viscosity of water at 20 degrees centigrade equal to 0.01 poise. So we need to find out the velocity and the rate of flow in the model. And here what are the questions are given. Okay, so that is for the prototype. Okay, prototypes are given and we need to find out the answer for the model. So first of all, here we'll see what are the data are given in this question. So at the starting we can write here. Let's write down the data given in this. So first one, the diameter of the pipe is given, that is D. Okay, so D equal to, we can write this is 1.5 meter, and similarly the specific gravity 0.9 it is given, so the specific gravity of oil it is given. So we can write specific gravity, that is 0.9. So this data for the actually is given for the prototype. These data are given for the prototype, and we need to find out the value, this velocity and this rate of flow in the model. Okay, and viscosity of the fluid is given, that is what are the fluid is taken here, that is oil. Okay, and specific gravity is given 0.9. so this is viscosity is given 3 into 10 to the power minus 2, and this is poise. And next is given the rate of flow is given, that is a discharge 3000 liter per second. So same thing we can write here. This also you can write prototype. This is for prototype, and discharge for the prototype is 3000 liter per second. 3000 liter per second. This can be converted into meter cube per second, that is 3 meter cube per second. And next, the tests were conducted on 50 centimeter diameter pipe using 20 degrees centigrade, and find the velocity. So what we need to find out? We need to find out velocity of the model and discharge of the model. These two things we need to calculate it. Now density of oil is given. Density of oil we can calculate because specific gravity is given, so we can calculate density of oil, or this prototype what is there. This equal to, we can write specific gravity into the standard density of that. So this is 1000. So that means we can write 900 kg per meter cube. So diameter of the model is actually given here. See, diameter of the model is given. This is the diameter of the model. So we can write diameter of the model dm equal to 15 centimeter. So this one we can write 0.15 meter. And similar temperature is given 20 degrees centigrade, and the viscosity of water. So that is, we can write viscosity of water it is given. That is, we can consider the viscosity of the fluid which is flows through the model. So that is given mu equal to 0.01 poise. So this one we can write 0.1 poise. We can write this one like 1 into 10 to the power minus 2 poise. Okay, similarly density of water we know. So density of the water which is flowing through this model, that is density of the model we can write here, or the water, that is 1000 kg per meter cube. So based on this our requirement, we have identified all this data which is given in this question. So now we need to apply the equation what we have calculated in our last lecture, so that we can find out. So the pipe flow, that we need to similar the dynamic similarities. we need to validate the dynamic similarities that is obtained for the Reynolds model number. So the prototype and model should be equal. So let's write the Reynolds number for the model and the Reynolds number for the prototype, both should be equal. So for the, by using the previous equation, here we can write, we know that RB, this is rho VD, rho VD, rho M, Vm by mu, this is M. This is for model. Similarly, this will be equal to prototype. So again, rho P, Vp and dP divided by mu P, because this is the formula for the Reynolds number actually. So similarly, we need to find out this value, like we can segregate these things in such a way. This is Vm by Vp. Vm, see this Vm, we can write Vm by Vp equal to, we can write this is dP by dm. Or you can write this is, suppose dP by dm, if you want to write, you can write also like Vm by velocity, and then this velocity take it to this side. And similarly rho P by, here you can, on behalf of this, we can write rho P by rho M also. Okay. This into, again the same thing will come like dP by dm also, which is nothing wrong. Then again here you will get mu M by mu P. So all these things terms we have written. I have taken this velocity term one side and remaining terms other side, because we need to calculate the velocity, correct? So what I will do here, I can write this, all these values, rho P. So density of the prototype, that is how much? That is 900 divided by model density 1000 into diameter of the prototype 1.5 meter and divided by diameter of the model, that is 0.15 meter. Similarly, viscosity of the model, that is 1 into 10 to the power minus 2, and this is 1, sorry, this is 3 into 10 to the power minus 2. So these are the values are given. Now if you solve this one, so we can find out what is that, yeah, finally let's see, this is if you cancel this one, then it will get 10. So we can write this like, you know, 900, or you can write this, yeah, 900 divided by 1000 into 1.5 by 0.15, that is 10, and this is will get 1 by 3. This will be get 1 by 3. So here also you can cancel this, and we'll get how much? 0.9 into 10, that is 9. So 9 into 1 by 3, we will get 3. So this is the value. Now again we can write this is Vp equal to the rate of flow, or we can say, we know that one condition we can write here, like, you know, suppose here, let me write this is QP equal to what? We know that Q equal to A into V, so area of the prototype into velocity of the prototype. This is the formula of discharge. So if I write this one, QP equal to AP by VP, because here see in this ratio I got the value of this 3. So now we can write what? We can find out here VP equal to Q by AP. So area, discharge and area. So from here we can find out what is the discharge of the prototype. This is value given 3. The value is given 3, and area of the prototype is pi by 4 into d square. This way you can write pi by 4 d square. D is given, that is 1.5 meters, 1.5 square. So now you can write this is 3 into 4 and divided by pi into 1.5 square, that is 2.25 will come. So finally we can calculate this and we'll get the value of like how much, let's see, 3 into 4 is divided by pi and divided by again 2.25, 1.69. So this is our velocity of the prototype. So you can write 1.69, this is meter per second. So this is the velocity of the prototype. Now put this value in this equation. So here we can write Vm equal to velocity of the model equal to, we got the 3 value here, so 3 into velocity of the prototype. So that means 3 into 1.69. So we'll get the value of the velocity of the model. So here what is there? Just multiply into 3. 5.09. 5.09 meter per second. So the same thing I'll write here, 5.09 meter per second. So this is the first requirement we have identified, velocity of the model, which is given in the question to identify. Next, second one is the rate of flow. So similarly, we can write here also again, because we know the formula, I can write this is Q model, discharge for the model equal to area of the model to velocity of the model. So area of the model, we know that pi by 4 into dm pi by 4, what is the diameter of the model, that's square, into velocity we have just now we have calculated, that is 5.09. So if you just multiply this, we'll get the value. So let's see how we'll get this one, like 5.09 already given into pi and divided by 4. Sorry, 5.09 into pi equal to something will get divided by 4. Okay, then we got the same value. Anyway, multiply 0.15 into 0.15. So this is 0.089. So let me write here. We got the value 0.0899. This is meter cube per second. Now we can convert this one into in terms of liter. So if you convert into in terms of liter, then we'll get 89.9 liter per second. So this is the answer. Okay, now as per the question, we have identified the velocity of the model and rate of the flow in the model. So here you can see both are like, these two things are different because your diameters are different is there. So because diameter of the prototype here it is given 1.5 and here the diameter of the model is given 0.15. So if that varies also there, you'll get the variation in the answer also. If you consider the similar conditions, then we'll get the similar answers for both. So I hope you understand this problem, how we have solved. Only the thing is we need to remember this formula, like this one, when we have derived this formula, that you can remember this, or else you can just remember this concept. We need to similar the Reynolds number of the model and the Reynolds number of the prototype. So remaining things is very simple. You can easily calculate this. So I hope you understand. If still you are having any kind of doubt regarding this, you can give a comment on the comment box. Thank you.